like it is recording. So 5.2, come on, number 14. All right, so you're looking at the average value. All right. When looking at an average value, remember that the average value is basically taking your weird curve and sort of evening things out and converting it into a rectangle. That's what the average value does. The average value is looking at some curve between A and B and saying, okay, if I could find the average Y value, the average value is a Y value, if I could find that average Y value and I drew a rectangle at that height between A and B, then the area of the rectangle would be the same as the area under the curve. That's what the average value does. To get the formula for average value, what do? You have to take the area under the curve, so that's the definite integral from a to b of f of x dx, and multiply it, or do what with it? Divide by area of the box. How am I going to get the height of the box? What is the area of a rectangle? Length times width, or height. If I'm trying to find the height, F average, what would I need to divide this by? Area divided by B minus A. That is the distance. So the formula, it makes total sense if you think about it. The formula is the area that you have, which is the same as the area under the blue curve, which is the same as the area of the green rectangle. They're exactly the same area. If I take the area and I divide by the width of the rectangle, that should give me the height of the rectangle, right? Area of a box, length times width, or length times height. Okay, so now we go back to the function. Find the average value of this function between -9 and 9. Okay, so to do this, and I know the problem is not calculus, the problem is algebra, all right? It's killing you. So, and it always does, that's normal. And we're looking between -9 and 9, all right? And then we will need to find all the C, where we have that average value. Okay. So basically what we need to figure out is what that function is. The reason I say is it's the algebra is because students typically learn their algebra in Cal 1 and Cal 2 because you can't survive without it. So either you learn it or you don't make it. I mean, that's pretty much the way it goes. But that's normal. What is the definition of absolute value? And yes, you need to know it.
Distance away from zero.
Well, I need the piecewise defined, the formal definition. What is it? If it is positive or zero, stays the same.
X is greater than 0, x is less than 0, equals -x.
Perfect. All right, so Robert's right. If x is greater than or equal to 0, leave it alone. If x is less than 0, take the opposite. So now what we're going to do is we're going to rewrite this function right here in terms of the absolute value definition, all right? So the first thing I'm going to do is I'm going to take the absolute value of 3x, and we're going to rewrite that one. If, and I'm going to give you the rules, 3x is greater than 0, I'll do that. If 3x is less than 0, I'll do this. What does the definition tell you to do? If the thing between the vertical bars is not negative, do you do anything to it? Leave it alone. If the thing between the vertical bars of the absolute value is negative, what do you do to it? Multiply through by a -1. So if we had more than one term, it'd switch all the signs. In this case, I only have one term, so it's -3x. All right? When would 3x be greater than equal to 0 compared to when it's negative? At what x value do these change? It's simple here. When is 3x going to be greater than equal to 0? When x is, can I divide by 3? What's 0 divided by 3? So basically my rule here is the same as it was up there because I only had one term. If I had another term, I would have to move the constant term first and then do the division, right? Solve for x. So now I have a rule, I know where these are going to split apart, which means that when I try to integrate this, I have to split it up between less than 0 and greater than 0. That's where I have to split it. So I'm going to be doing the integral from -9 to 0 plus the integral from 0 to 9, because that's where this is going to change. Just the absolute value part. Now what about the rest of it? Because this is not the function. The function is 27 minus that. So if I'm going to do 27 minus that, what would my definition for f be? 27 minus absolute value of 3x would be, well, if x is greater than or equal to 0, it's 27 minus 3x. Just use that part. If x is negative, what is it? 27 minus a negative 3x, which makes it 27 plus 3x. Okay? Now that's doing it algebraically. So the next part, of course, is to take each of these and plug them in over here for the integrand. Oops, I got them backwards. Oh, that's okay. Make that one the plus, and that one the minus. Does that make sense? That's doing it algebraically. You can also do it graphically. If you think about the rules that you had before for your translations and shifts, stretches, all that stuff. If you think about what is the absolute value of 3x going to look like, so you start with absolute value of 3x, which definitely when x is 0 is 0. What is it when x is 1?
3.
3. And when x is negative 1?
3.
3. Good. What did you do to your absolute value? You stretched it vertically because you multiplied it by a constant, so that stretched it vertically. What does multiplying it by the negative do to it? You just reflected it across the x-axis, so now I've got absolute value of 3x times a negative 1. That's going to flip it upside down, but it maintains the same shape. And then what does adding 27 do to it? It's just the whole thing up 27. So if I have 27 minus the absolute value of 3x, boy, this is going to be a bit of a challenge. Okay, so way down here somewhere. And up here I've got 27. So it's here, and I'm going to go down 1, 2, 3 to like that. Does that make sense? It looks something like that. Okay. Same basic shape. This gives me two lines, right? They both have the y-intercept of 27, agreed? What's the slope on this one? I mean, what did you say? You're going to go up 3 and either left or right 1. So if it's a change of vertically 3 over 1, it's got to be a slope of 3, either positive or negative. Which one is the left side? Is that the positive or the negative? That's the positive. So I have 27 plus 3x on the left side. What do you have on the right side? 27 minus 3x. Isn't that what we already got? So you can do it algebraically, you can do it graphically, but this is all, it's complicated, right? This is not simple stuff. But it's basically using the formal definition of the absolute value. It's tricky. I think the easiest way to do it is literally to go one step at a time, right? Either if you're going to do it graphically, go one step at a time. Even if you're going to do the absolute value, write the absolute value of x first, then apply it to just the absolute value part, right? So you get that definition. This is going to be whatever's between the bars, no change. This is going to be whatever's between the bars, put in parentheses with a -1 outside. This is going to be what's between the bars greater than or equal to 0, solve for x. This is going to be what's between the bars less than 0, solve for x. This number becomes the number where you split the integral into two pieces. Does that make sense?
And
Okay.
For finding the average
Now this is just for finding what?
area.
This gives me the area under the curve, right? And then what do I have to do in order to find the average? I think I still have it up here. Multiply it by 1 over b minus a, and that will give me the average value, okay? Which if you're looking at the graph over here, I mean, x needs to be 9 or -9, right? In order to intersect the x-axis, so down here at 9 and -9, eyeball it and tell me where you think the average value is, roughly.
0.
It wouldn't be 0, that would be down here. Draw me a rectangle. How high should the rectangle be, roughly? Just take a guess. Between -9 and 9, I'm guessing something like that. This part is under both curves. This is not, but I got to make up for these parts up here that are left out. So I would guess somewhere about halfway in between 0 and 27. So I would expect anywhere from 10 to 17 to be the average value, something like that. Okay? Does that make sense to everybody? The actual answer is 13.5, which is, I think, exactly between 0 and 17, isn't it? Okay, but that's mostly because I've been doing it in a long time. I just have a good feel for it. So this together gives you the area, and then you're going to multiply by 1 over b minus a. Make sure you get the right minus for the formula. A is a -9. Do not give me 9 minus 9. You know that can't be right. If it were 9 minus 9, you wouldn't have an average value. But I can draw it, so it has to exist, which tells you have an error somewhere, right? So this would give me a difference of 18, right? So this would be 1 over 18, whatever these come out to be, okay? And that would be the average value. And then the next part you would have to do is you take that average value, which I think I said is 13.5. So you've got 13.5, which is f of c. Now you have two sides, which means I probably have two places that have that value. Does everybody see that? Over here, I'm going to have a C1, and here I'm going to have a C2. Two places that have that y value as their function value, 13.5. One on each side, right? The geometry of the problem should really help you to solve it, right? Use the geometry, draw the pictures. The pictures are important, okay? So in order to do that, how are you going to find the two C's?
You just plug them into their
respective sides. So again, come back to your formal definition for the function using the definition of the absolute value, or if you did it geometrically, come to each side of the absolute value function and use each line. Either 13.5 is equal to 27 plus 3x, or 13.5 is equal to 27 minus 3x. Those are the two sides of that piecewise defined function. And then it's just, I mean, that's just straight algebra, right? I mean, that's not anything terribly difficult. If I subtract it, let's see, what do I get? It is Monday. What's 13.5 minus 27? Is it 27 minus 13.5? 13.5? Okay, good. Whew. Okay. Minus 13.5 equals 3x, so this x is a negative 13.5 divided by 3. I don't know what that is. 4.4-ish or something like that, 4.5, which, okay, yeah, I'll buy that. Maybe about halfway. And this one is going to be, I'm going to move the 3x, and that will give me 13.5. It's the same value on the other side. Why are they the same value on the, why are they the same?
Because it's symmetrical.
Symmetric. So here you can use the symmetry of the problem. You could have done half the problem and then be done, right? You could have done that. You can use the symmetry to figure this out. If you know the graph is symmetric, could I have just cut off this entire left side and just looked at the right? Yes, I could. I could find the average value of the one on the right. I could find the place where that occurs and then reflect it. It has to be the same. Because the amount of area on the left side is exactly equal to the amount of area on the right side because it is y-axis symmetric. We have a word for that. When they're y-axis symmetric, what do we call them? They're blank functions, 4 letters. 2 of them are e.
Even.
Even. Yeah, x squared, right? Your basic, this is the y-axis, right? Just fold it on the y-axis and they touch, right? And this is clearly one of them, right? So you can use that even odd even when you're not finding area specifically, even if you're looking for average value, it still works, okay? All right, let's move on. So this is actually a good one. I'm glad you asked about that one. It's kind of a fun one. Can you come back on? No? There we go. All right, let's move on to substitution. We need to talk about how to deal with problems where you can't directly integrate because the antiderivative doesn't work out exactly. Okay. Actually, maybe I don't need the overhead. Think about it. All right, this is what we call U substitution, or the substitution rule for short. Let's suppose that we have some function f, and we know it's antiderivative. Let f of x have antiderivative f of x. Okay. Now again, that means that f undoes the derivative. So f prime, capital F prime of x should give me back f again, right? So let's put that over here in parentheses. So f prime of x equals f of x, right? That also means that the integral of f of x dx is equal to f of x up to a constant, right? It's one of the antiderivatives, but there are infinitely many antiderivatives for any function that's integrable, right? So those are the two relationships we have if we say that capital F is an antiderivative. All right, here's the issue that we have. How are we going to deal with a composed function? That's our problem. So let me give you an example of that. Let's suppose that we let f of x equal, let's do a simple one, 2x. Yeah, 2x. All right, very simple. find me an antiderivative for 2x. Any antiderivative, I suggest you pick the easy one where the constant is 0. Integrate that, right? Antiderivative, what is it? X squared, right? You divide by 2 and multiply by 2, but the 2's cancel, so you just get x squared. So if that's the case, then f of x is x squared, all right? So what I'm proposing over here is, what if it's not 2x? What if it is 2 times, what would be an easier one? Cosine. Something like that. Or you can even nest them, and you could do something like that. You have a function and a function, right? Does that make sense? If I made it more complicated, you would tell it's not this one you could have done without using U substitution, but you would have had a harder time on the next one. What if I had done 3x squared? Give me an antiderivative to 3x squared. X cubed. Now suppose that I had asked you to integrate 3, what is I going to use? Cosine squared of x dx, or something like that. This is a problem. The format is still 3x squared, but the problem is the thing on the inside is no longer x, it's another function, right? We have a composition of functions, and how do we deal with a composition of functions? In order to do the composition of functions, we need to remember where this came from. We're trying to undo the derivative, so let's do the derivative on a composition to remind ourselves what we have to do. So what is the derivative of a composition? Let's say that we had undone the derivative, so we have capital F of x with g of x on the inside. How do you do the derivative of a composed function? What rule do you use for derivatives? Chain rule. And what is the chain rule going to give you? Derivative of the outside, f prime. What do you do to the inside? Keep it the same. So g of x times, and that's a times, not a composition. Make sure it's a filled in ball. Times what? G prime of x. All right, that's how we would do the derivative. This is chain rule. So if we have that, but what did we say about capital F? Capital F is one of the antiderivatives of lowercase f, which means that f prime, capital F prime, is lowercase f, is it not? So can I replace this with lowercase f of g of x times g prime of x? Does that work? Given that capital F is an antiderivative. What does that tell you? That tells you that f of g of x is an antiderivative of this thing, which means that over here, if I'm going to be able to integrate this, there has to be more here. I do have f of g of x. Does everybody see that? If I let f be 3x squared and I let g be cosine of x, do you see that I have 3 times cosine squared of x? This part is f of g of x, composition like normal. But what am I missing in order to complete the integration? G prime. What's the derivative of g? What's the derivative of cosine? Negative sine. I would have to have another factor of negative sine of x or sine of x to be able to do it. I don't have to worry about the negative because I can always put in and take out the negative if I want, right? By multiplying by -1 over -1, right? This is what's called U substitution. here's the basic rule. If you have the integral of lowercase f of g of x times g prime of x, you have the integral of a composed function multiplied by the derivative of the inside, right? Composed function times derivative of the inside function, then the original antiderivative with the g of x plugged in becomes a antiderivative for the composition. So this is going to give me f of g of x up to a constant. All right? Now, where does it get the name substitution or u substitution? What do you suppose I'm going to let g of x become? Let g of x be u. So I'm going to let g of x equal u, and then the integral of f of g of x times the derivative of the inside can be written as f of u times u prime dx, or u du, du dx, which becomes f of u up to a constant. Let's do some so that you get the hang of it. All right. Now, this doesn't work for everything, but it is probably one of the most effective tools we have for integration. So we're going to leave that up there. I'm going to work a couple. And I'll leave this one at the bottom so you can see that one. Let me show you what it looks like. So we'll do an easier one first, and then we'll go back to that harder one we created. Let's suppose that I gave you the integral of e to the 3x plus 1 dx. Just like you did when you were doing the derivative, you need to locate the inside function and the outside function. The outside function is the last thing you do, right? How do you know what's on the outside? It's the last operation that takes place. If I gave you a number for x and you plugged it in, the first thing you do is multiply by 3, then what? Add 1, got a number, now what? E to that number power, that's the last thing you did. So the outside function, our f here, is e to the u. What's inside of it? What did you do before you did that? 3x plus 1. So my g of x is 3x plus 1. So that f of g of x is e to the 3x plus 1. Is everybody okay with that? All right, so if I'm going to do that, what I'm going to write, and this part right here, we typically do not write. We'll write it today because we're learning it, but typically we don't write it. The next part we do write. What is u? U is the g of x function, which is 3x plus 1. I want you to take the derivative of that with respect to x. We're going to abuse notation again, all right? What is the derivative of this with respect to x? Yes, it's really easy. It's just 3. Now I need to abuse the notation because I need to get a dx. I'm going to replace the 3x plus 1 with e to the u, but the problem is when I switch from x to u, I can't use the same differential. If I change the variable, I have to change the differential. What differential is going to go with u? du. What do I currently have? dx. Let's abuse the notation. I'm going to move the dx over here to the right side. So I get du equals 3 dx. Do you have a 3 times dx in that problem? No. Well, then keep abusing it and solve for dx. What do you get? Dx equals du divided by 3. And we're going to substitute in place of dx, du divided by 3. Now the divided by 3 is just a constant of 1/3, so what can I do with it? I can pull it outside to the front. So if I pull that outside to the front, I have the integral of 1/3 of e to the u du. What is the integral of e to the u du? It's e to the u plus a constant, right? Don't forget about the 1/3 at the front. So I have 1/3 e to the u plus a constant. And some students ask me, well, why don't we multiply the constant by 1/3? We are. You do. But what is 1/3 of a constant? It's another constant. So we just roll it all together and just call it plus c. Because we don't know what c is anyway, right? So we roll it all together. This is what you get for the second to the last step. The last step is the original problem had x for the variable and dx for the differential. You need to go back to x. What would you do here to get back to x? Back substitute. What's u? So you get 1/3 e to 3x plus 1 plus a constant. That's it. That's your integral. Now I have some students that don't like this sort of abusive notation over here. They consider it sort of trickery. They don't understand why is this working. So I'm going to show you why it works. But then after that, I think you'll trust that it does work and you'll just do it. It is easier. All right. So what we're starting with is e to the 3x plus 1 dx. And we decided that u was 3x plus 1. So the derivative of that with respect to x was 3, right? In order to do this, I need this g prime of x in there. Do I have a 3 in here? What are the two things you're allowed to do anywhere, anytime, as much or as little as you want? Add 0. Multiply by 1. I need to multiply by 3. So I'm going to use multiply by 1, and I'm going to multiply by 3 over 3. Isn't that the same thing? And then I have the differential. I'm going to include the 3 dx to serve as my g prime. So I have f of g of x, e to the 3x plus 1, times g prime of x, 3 dx. And the 1/3 isn't included, so it floats to the front. Does that make sense? And that's why I end up with 1/3 e to the 3x plus 1 plus a constant. I do it both ways. I will say that sometimes you have part of the derivative, but not all of it. And what I'll do is I'll actually circle the parts that are part of the derivative of the inside function so that I know which parts are not in it, so I know to bring them to the outside. Okay? And I expect we'll see some sort of like that. Okay? Let's do some more. All right, I'm kind of a visual person, so I like to draw circles and make sure I can identify parts. Okay, how about this one? The integral of the cosine of 2x plus 5 dx. Identify inside for me, identify outside. Outside, remember, that's our f of x, and inside, that's our g of x, which is otherwise known as u. What's my outside function? Cosine. What's my inside function? 2x plus 5. I will say there are some integrands that can be done more than one way, all right? There are some integrands where the way you split it up into inside and outside can be done a couple ways. There's usually an easiest way, all right? Look for major operations to split them up. Parentheses, powers, things under a radical, the argument to a trig function, those are the inside function, argument to a natural log, those kinds of things make good inside functions. Okay, if u is 2x plus 5, what's du dx? 2. Let's abuse the notation and solve for dx, because that's what I have up here. Does everybody see that? All I have is f of g of x. I do not have g prime of x. This part right here, that's my f of g of x. I'm missing my g prime of x. I do not have it. I need to put it in. So I'm going to solve for dx, which basically becomes du divided by 2. So this becomes the integral of the cosine of u times du divided by 2. Where does the 2 go? Pull it to the outside. In derivatives, we didn't do this very often, pulling that constant out, but in integration, you do it all the time. It's much simpler to get the constant outside. So we have 1/2 the integral of cosine of u du. What is the integral of the cosine of u du? What function's derivative is cosine? Sine. So this is 1/2 sine of u plus constant, but the original had a differential of dx. X is the variable, get out of u, go back to x. What do you have? 1/2 the sine of 2x plus 5 plus a constant. Okay? Everybody with me so far? No one's freaking out yet. Okay. Let's up the stakes a little bit. The integral of x e to the x squared dx. Again, this can be really intimidating because you see the x times the exponential, and that makes you think that's not composed, right? There's no way that I'm going to be able to work this because that's not composition, that's multiplication. It's a product. But hang on, the main thing here is the e to the power. What would u be if you were just looking at e to the power? X squared. So if I let u be x squared, what would my du be? Du dx would be 2x, right? And then we abuse the notation. And I will tell you that I'm having a very hard time writing it this way because most of the time we start off with the second line. We know we're going to abuse the notation, so we just swing the dx to the other side from the very beginning. Do you have any of the pieces of this g prime of x already in the integral? I have x dx. Do you remember I said I sometimes circle the pieces that are part of the derivative of the inside? This x dx, do you see that part right there? That is part of g prime of x. What am I missing? The 2. So I abuse the notation, I solve for x dx, and that gives me du over 2. The x dx that I circled is going to be completely replaced by du divided by 2. So this becomes the integral of e to the u du over 2. What's the integral of e to the u du? E to the u. And the 1/2 is still there. So I get 1/2 e to the u plus a constant. And I go back to x, so I get 1/2 e to the x squared plus c. Everybody okay with that? This next one is really tricky. I know when I was learning these were probably the ones that took me the longest to recognize that this is what I needed to do, all right? I'd seen the trick, but it just took me a long time to figure out, oh, this is where I need to use that trick, all right, the next type. So here is the integral of the square root of x plus 1 to the 4th power divided by 2 square root of x dx. Actually, this one may not be too bad. No, this one's not it. I'll find another one later on that uses this one. Okay, anybody want to make a guess? I mean, there are different options here for you, right? Anything raised to a power, the base is a good choice for you, if that's where the variable is. If this had been a constant and the variable were in the power, that would have been a good choice. But fractions, the denominator is also a good choice for you. So again, it takes a little bit of experience to sort of predict ahead which is part of the derivative of the inside function, or part of the g prime of x, or the derivative of u, and which is actually a part of the composition. What might help you here is to remember what's the square root, or what's the derivative of a square root? 1 over 2. Isn't this the derivative of a square root? Then it looks to me like this is part of g prime. This is part of du, which means something up here has to be u. What would you choose for u?
Square root of x.
That's correct. Square root of x plus 1. You have u to the 4th power is what it would basically end up being. Now, we're going to abuse the notation and slide the dx to the other side from the very beginning. So what's the derivative of u with respect to x? What's the derivative of square root of x? 1 over 2 the square root of x. And the derivative of 1 is 0. And we're going to slide the dx to the other side. Do you have that already in your integral? Yep. I would circle it. That's what I like to do. That way I know I haven't missed anything, right? I circle my du so that I have the integral of u to the 4th du. What is the integral of u to the 4th du? What do you do to the power? Add 1 and divide by it. You guys are like, okay, don't let it freak you out. It's the same power rule in reverse, right? Now get out of u and go back to x. Square root of x plus 1 to the 5th power divided by 5 plus a constant. Questions about that one?
If you chose a different u, would it still work?
Sometimes yes and sometimes no. So there is an art to choosing the right u. There's almost always an easier way. And there are times if you choose the wrong u, it won't go. And then you know you've got the wrong u. Okay. Let's do another one. Let's suppose I gave you this one, and then we're going to do a definite integral. You should recognize this one. I think this is this cotangent, I think, or is it tangent? I always get them backwards. This must be tangent, right? Because sine see, a cinch has the negative, right? So remember back very beginning of the semester, we did hyperbolic trig functions. You're probably like, no. Okay, e to the x minus e to the minus x divided by 2 is sinh. E to the x plus e to the minus x divided by 2 is cosh. So this is sinh divided by cosh, which must be tanh. You don't need to know it in order to integrate it, right? But this is it, okay? So if you do remember what the derivative of tanh was, it might help a little bit, but if you don't, it's okay. Which one is u? What's u? When all you see is a fraction and you don't have a power like this or a trig function or something else, typically u is going to be the denominator. All right? So when you have just a fraction, you typically have the denominator being u. Why would it be the denominator that's going to be u?
It's the last thing you do.
It is the last thing you do. It's the divided by, but what's the other part? What function do you know that has a derivative of 1 over something? Natural log. Right? The last thing you do is the division, and you know a function whose derivative is 1 over something. All right? Natural log. So we're going to choose u to be the denominator, e to the x plus e to the minus x. We're going to take the derivative with respect to x, the original differential, swing the dx to the other side. What is the derivative of e to the x? That's an e to the x. What's the derivative of e to the negative x? This is negative e to the negative x. This is chain rule, right? Because you have an inside function negative x. So you do the derivative of an exponential is the exponential, e to the negative x, but then you have to do the derivative of negative x, which is negative 1. And that gives you a negative out front. This goes in parentheses with the differential outside, right? Because it's that thing times the differential. Remember, the differential would originally have been under du, and we swing it around to the other side through multiplication. So it goes in parentheses. Do you have that in your integral? You do. This entire numerator is du. So we do straight substitution. This is the integral of 1 over u du. What function do you know whose derivative is 1 over u? Natural log. So we're going to have natural log. Now you're going to notice that I'm going to put absolute values around it. Why did I put absolute values around the u?
Natural log can't be negative.
Natural log cannot be negative. And when we do the reverse of the differentiation, we have to force whatever was on the inside to not be negative. So the absolute values are a part of the antiderivative for natural log. Anytime you integrate and you get natural log, you should have absolute values around the argument. The only time you can drop them is if the argument is for sure positive, like x squared plus 5. There's no way to make that negative. Then you could drop them. Otherwise, these absolute values have to be there. Then go back to what the original u was, which is the natural log of the absolute value of, where did it go? E to the x plus e to the minus x plus c. All right? Now, I said if you knew that the argument was positive, you could drop the absolute values. What do you know about the graph of e to the x? What does it look like? Like that? Does it ever go below the x-axis? Never. It's always positive. What about the graph of e to the minus x? That's this one. It's a decreasing, right? Radioactivity gets lower and lower amounts of radioactivity, but it never goes to 0. It never goes below the x-axis. If you add two strictly positive things together, what do you get? Strictly positive. So we could drop them here and write it like this. You cannot go further. I know it's tempting. It's natural log with an exponential inside of it. But this is addition, not multiplication. Logarithms split across multiplication and division. They do not split over addition or subtraction. Okay? So don't make that mistake. Let's look at a definite integral, because we need to talk about how to do those. And tomorrow I will probably find some of the trickier ones and pull those in and do those. Okay. I want to take a look at the integral from 0 to 2 of 2x over x squared plus 1 quantity squared dx. I am not looking for an antiderivative function. What am I looking for? What am I going to get with a definite integral? A number. One finite real number. Or it'll blow up to infinity, but honestly that's not going to happen to you guys until you get into Cal 2, and then things do blow up all the time. This is going to give us a finite real number, and that number represents what? The area between the curve and the x-axis, between x equal 0 and x equal 2. This has a graph. Whatever the graph looks like, we make a vertical line at x equals 0, a vertical line at x equal 2. We look to see where that intersects the graph, and then we shade all the area between the curve and the x-axis. This will give us net signed area. If it were a velocity function, it would give us the displacement, how far away from the starting point we are. Now, the problem here is that when I switch out of the differential dx, I change the variable from x to u. Now on the indefinite integral, that was fine. At the end, we just went back to the original. It was no problem. We have a problem with the definite integral because I am supposed to, at the end, plug in these limits of integration. Am I not? And what kind of numbers are the limits of integration? X values or u values? X values. You have two choices. I use them both. It depends on my mood. I would say I tend more towards one than the other. It's up to you. You can do it either way. So I'll work it both ways and then you get to choose. Method 1, switch to u, but don't switch the limits of integration. All right? In this problem, what do you think the right choice for u is? X squared plus 1. Two reasons. One, it's the base being raised to a constant power. That makes it a good choice of u. Two, it's in the denominator. Three, what's the derivative of x squared plus 1? Which I can see right there. All right, so I'm pretty confident x squared plus 1 is u. Take the derivative, swing the dx around, and I get 2x dx. That right there, that's my du. I like to circle them. We're going to rewrite it. This becomes the integral of 1 over u du. I've now switched in the integrand and the differential to u things.
Would it be 1 over u squared?
Oh, my bad. Yeah, 1 over u squared. But I'm not going to switch the limits of integration. If I don't switch the limits of integration, then I have to label what they are so I don't forget that I haven't done it. So I write x equals 0, x equals 2. I haven't changed them. They're still x values. But if I don't write x equal, I'm going to forget, I'm going to think they're used, and I'm going to plug them in and get the wrong number. Okay? So for this one, the easiest way would be to rewrite it with a negative exponent. So u to the negative 2 du. What's an antiderivative to u to the negative 2? Add 1 to the power, negative 1, divide by it. This would give me negative 1 over u, or negative u to the negative 1. Power rule in reverse. Now normally for an indefinite integral you'd have a plus c, but this is definite. So I want to evaluate it between x equals 0 and x equal 2. What are you going to do before you can plug in? Substitute back to the x version. So get out of u, get back to x. So I have negative 1 over x squared plus 1 between. Can I drop the x equal on the limits of integration now? Now I can drop them because it's back to being an x thing. So from 0 to 2, which gives me, plug in 2 first, negative 1 over 2 squared plus 1, minus for the formula, the thing is negative 1 over 0 squared plus 1. I'm getting negative 1/5 plus 1. Is that what you were getting? 1 over 1? Which gives me 4/5. Is that what you guys got? Okay. Other way to do it. Ooh, wow, I'm out of time. Switch the limits of integration. Change them. If x equals 0 and u is x squared plus 1, what is u? Plug it in. What do you get? 1. If x is 2, what would u be? 2 squared plus 1 is 5. Then you would integrate from 1 to 5 of u to the negative 2 du. Change your limits of integration and make them u values instead of x values. And when you're done, you should get the same thing. But in this case, you would be integrating negative 1 over u between 1 and 5, which would give you negative 1/5 minus a negative 1 over 1. Am I not getting the same thing? It's your personal choice which way you do it. I use them both. It just depends on how complicated it is to go back and forth. Okay? So we'll stop here. I do have your exams.